Welcome back to Wichita State University's Lifelong Learning Program. I'm Heather Merchant, and this is the Geology of Natural Disasters. But before we get started today, I've been asked to take care of a few housekeeping items. About halfway through, we're going to take a bathroom break, so that'll be about 10 minutes long. And if you go out these doors here, the ladies' room is to the right and the men's room is to the left. So they're very close. If you're in the online class and you'd like to submit a question, please do so by email and they'll be printed and given to me and I can answer your questions. And although it's wonderful to be around people again and be here in person, we need to remember that Wichita State University has a policy for face coverings. All students, faculty, staff, and visitors must wear face coverings over their mouths and noses while on all Wichita State University campuses, in all hallways, public spaces, classrooms, and other common areas of campus buildings. So just remember to keep your masks on and we're all good. Okay, so we're already in week 2, and we're going to cover earthquakes and tsunamis. And one of the students already let me know that we covered volcanoes last week, and one of the students let me know that there was a volcanic eruption in Indonesia that was pretty significant this morning. So if any of you want to read about that later, it's great timing. And yesterday morning, there was an earthquake in North Carolina, so we'll talk about that a little bit later as well. But Mother Nature seems to be in tune with this class a little bit, so maybe next week we'll have a landslide somewhere. Not that that's a good thing, but we can look at it if it happens. So we're going to cover the causes of earthquakes, the seismic waves from earthquakes, how earthquakes are located and measured, the effects of earthquakes, and a tsunami can be an effect of it. As we learned last week, volcanic eruptions can also start a tsunami. We're going to look at a couple of active fault zones within the United States. We'll look at a few historic earthquakes and watch little short videos showing some actual footage from those. I really had to trim it down because there's so many noteworthy ones throughout history that I wanted to cover, but we only have 2 hours, so I only have about 5 in there. Then we'll look at earthquake predictions and how accurate those are, mitigation and survival tips for living with earthquakes, and then the fun part, we'll take a look at some local seismic activity, and maybe some of you have, in the past few years, have felt some of the earthquakes that we've had here. So there's about 1,000 earthquakes that happen around the globe every single day. Well, we don't hear about many of those on the news. I mean, it can be years in between a major earthquake. So most of those are pretty insignificant. A lot of them probably people can't even feel. But the fact that there's 1,000 every day shows us that the planet is really moving. We're having a lot of movement. So we all know what an earthquake is. We know that there's trembling and there's shaking. And if you go back to last week when we started and we covered plate tectonics, the plates are similar to a broken eggshell on the surface of the earth. And things are moving apart at spreading centers. They're coming together at subduction zones. Things are being pushed and pulled. So there's a lot of energy there. And the plates and rocks are not smooth and even. They don't just glide past each other nicely. It's very rugged and jagged, and things get stuck and pressure builds up. And it'll go like that, and it can't move, and it can't move, and pretty soon it'll break loose. And when we have that abrupt movement, things get ruptured, and that's when we have an earthquake. So if you remember from last week, we had 3 different types of plate boundaries that we covered. So at the plate boundary, we can be moving apart, we can be pushing together, or we can be sliding past each other. So there's 3 different types of faults. Now, the faults are not necessarily at plate boundaries. The plate boundaries are a type of fault, but faults can occur elsewhere and at different scales. A fault can be anywhere from a very small crack that you can see in the rocks where there's been some movement to the largest scale of subduction zones. So the 3 types are normal, reverse, and strike slip. And these correspond to the 3 types of plate boundaries that we discussed previously. So looking at normal faults, and there we go. Okay, so normal faults, things are pulling apart. So we have extension. Now, if you look at the image of the rocks, the photograph, you can see that there's a diagonal line through it. That's the fault. And you can see that the layers in the rocks, they don't match up. So on the section to the right, which we call the footwall, it's moved upward. And the reason why it's called the footwall is if you go hundreds of years ago to the first miners, well, even today, a lot of mines are created along fault zones because that's where we have things get heated up, fluid can come up, we can deposit minerals and they become veins. So that's where a lot of mining was done. Well, the first miners that would mine in these faults, they would be standing, if you drilled directly where the fault was, you'd be standing on one block, so that would be your footwall. And from the photograph, you can see that would be the chunk on the right. Now the other one, the part on the left, that's called the hanging wall. And that's because they would hang their lantern up on that block. So that's where we get the names. But in a normal fault, we have the footwall moving up. And there's a little animation here, and it'll show you the movements so you can see them happening. And I think the internet's a little slow again. There we go. So the footwall is moving up and the hanging wall is moving down. And in the animation, the footwall and the hanging wall were exactly opposite of what we witness in the photograph. So a reverse fault is exactly what it sounds like. It's the exact opposite of a normal fault. So reverse faults occur where we have compression, where things are coming together. So it could be a convergent plate boundary. So we have just the opposite movement. So now we have the footwall moving down. And you can see that in the photograph where the layers aren't lining up and the footwall is below. It looks like that might be like a layer of chert, that big banding there, but it's moved down. And here's an animation of that motion. Yes, everything's going very slow today. Okay. And the third type is strike slip. So this correlates to a transform plate boundary. So there's no vertical movement. Things are just sliding past each other. Now, what's interesting is you can have a right lateral or a left lateral. And this is kind of fun. It usually confuses first-year geology students. But if you look at the aerial view of the transform fault, the photograph, and just pick one side of it and pretend you're standing on that side and you're looking towards the fault. Are the landforms moving to your left or to your right? With this one, they'd be moving to your left. So we would call this a left lateral. And the fun part is, it doesn't matter which side you're standing on, it's still moving to your left. So a right lateral is just the exact opposite. So it's one of those things that it's quite simple, but students tend to overthink it and then they start getting confused. But it's just whatever you're looking at, whether it's moving to your left or to your right. And so here's a little animation, and this animation is left lateral, so it's exactly what the aerial photograph is. And as it's moving, the stream is having to find a new path. And that happens quite often along these faults. Sometimes when there's a strike slip fault and like a farmer's field or something, and they have a fence across it, after it moves, the fence is broken and it's in two different locations. Okay, so those are the type of movements we can have, but why are we actually shaking? In 1906, Harold F. Reed was studying the aftermath of the San Francisco earthquake, and he wanted to find the mechanism for the shaking. You know, they didn't know that much about earthquakes back then. Plate tectonics was not a thing. Nobody really knew how plates moved, or where earthquakes or volcanoes came from. But he did do some research on shaking and how things break and move. And this is much like a rubber band. So as things are being pulled and moved, as you can see in the second street down, pressure begins to build up in them. So it's strain energy, and it's building up and it's building up. So when it ruptures, this energy is released. And the energy is released in 360 degrees all the way around. And that energy is the waves, the seismic waves, and that's what we feel, that's the shaking. So he came up with a theory of elastic rebound theory. So if you think about a rubber band, when you pull it so tight that it finally breaks, it doesn't just break nicely and just calmly hang down, it'll snap and move. And that's basically what his theory is. And then after a while, it stops moving, and we have the third street at the bottom, and things are no longer in the same place where they were before. So that brings us up to the seismic waves. So once you have that break and that energy is released, the energy is the seismic waves. So before we look at the actual waves, we need to know the difference between the focus and the epicenter. Now, we've all heard about the epicenter. We've all heard that term. That's always on the news. Anytime there's an earthquake, they always tell you where the epicenter was. The only difference between the two is location. So the focus is where the actual break occurs along the fault. So that's deep within the earth. The epicenter is that spot just pulled up to the surface. So it's the spot on the surface that's directly above the focus. And although we can pinpoint the epicenter pretty accurately, it's much more difficult to know exactly where the focus is, as you could imagine. You can estimate the depth, but it's hard to know exactly where. So with seismic waves, we have two different kinds. We have body waves and we have surface waves. And their names are pretty descriptive. Body waves radiate out and go through the earth and come to the surface. Surface waves travel along the surface of the earth, so they'll go around the globe. P waves are called P waves for primary. So that's the first wave that's going to arrive at a certain location. And S waves are secondary waves, so they're the second that are going to arrive. And they have different movements and they do different things. So the primary waves can pass through solids, gases, fluids, but the S waves can't move through any liquids. So if you're on the ocean, on a lake, on a boat, even in a swimming pool, and an earthquake occurs, you're going to feel the primary waves, but you're not going to feel any secondary waves. Because once that wave hits the water, it bounces off. It can't go through the water. Primary waves move longitudinally. So imagine a slinky or a spring, and we're moving that direction, but we're compressing and going this way. So we're moving horizontally, we're not moving up and down. S waves are just the opposite. They are going to go, imagine you have like a rope and you kind of do that action with the rope, and the rope is tied to something at the other end. So we're traveling that way, but we're going to go up and down while we travel. So those are secondary waves. And they both are destructive, but secondary waves are much more destructive, as you can imagine. When you're moving things up and down, as opposed to this, it's much more damaging, especially to buildings, infrastructure. So here's a diagram of the wave motions. So the particles in P waves are moving back and forth, and the S waves are moving up and down. So here's a little animation of S wave movement. So we've all experienced that movement at some point, probably at least in our childhood, where you're, swinging the hose or a rope or something, and we've seen that movement. And there's two kinds of surface waves. So we have love waves, very nice name. They don't have any vertical displacement either. So they're moving side to side on the ground, sort of like a snake, very sinewy, sort of side to side as they're going. Again, they can't travel through liquids. So if you're on the water, you're not going to feel these. But as you can imagine, they're pretty destructive. If you take the ground and go back and forth under a building, you're really going to shake it. You're going to cause some major damage. And then there's Rayleigh waves. They act like rolling ocean waves. So the particle would actually be rolling along. So they're an elliptical movement, and they move opposite to the direction of the wave. And again, these are very destructive to buildings. And in the next slide, I've got little animations of them as well. If we get to the next slide, there. So this is the love wave. We'll watch that one first. Maybe we'll watch it. It won't play. Well, I'm sorry, it won't play. But you can see from. Oh, okay. Now it's going to play. So you can see how that would be very destructive. There's a lot of movement and a lot of motion going on with that one. And this is the Rayleigh wave, and it rolls like the ocean. So sort of a compression up and down type of movement, a very rolling movement. And again, that can be very destructive as well. Okay, locating and measuring the earthquakes. So usually within like minutes of an earthquake occurring on the news, they'll already know where the epicenter of that earthquake was. And I will show you how they get that. Okay, so we've all heard the term seismograph, and these were very simple devices that were invented, just like a pencil hanging, and as the earthquake shakes, it would put the lines on the paper and the paper was pulled through. Now they're much more complicated and electronic, but they record the same thing. And the paper that they're recorded on was called the seismogram. Now those are electronic, but it's still called the seismogram. So if you're looking at this one, it demonstrates where the P wave is, the S wave, and the surface waves. They always come in that order. And you can see by looking at it, you can tell where each one of them starts and stops pretty easily based on the curves that you're looking at. So the P waves and the S waves, they radiate out from the focus at the same time. As soon as that break occurs, they start radiating out. However, they move at different speeds, and one of them bends and the other one doesn't. And that's because one of them doesn't go through liquid. And if you remember from last week, we learned that the inner core is solid, but the outer core is liquid. And so it bounces off that. So because they travel at different speeds, we can record the time at any given point on Earth where we record the time when the first P wave arrives and then the time when the first S wave arrives. And if you take the time interval in between those two arrivals and you look it up on a chart, it'll give you a distance. So as you can see from this one here, we've got from when the first P wave arrived to the S wave, we have 3 bars, and the bars are 1 minute each. So in this situation, it took 3 minutes in between them. So we would get our chart of the intervals, and we would look up what distance correlates to 3 minutes in between that P and S wave. So we would need to do that for 3 or more locations. Then what we do is draw a circle around that point where we took the recordings. And you need to do that with 3 locations, and the radius of each circle is equal to that distance that you looked up. And then once you do that, they will meet at a particular point. That point where they all cross, where all the circles cross, that's the epicenter. So it only takes a few minutes after an earthquake and they know where the epicenter is. So this is something that hasn't changed in many years. It's something I like it because it's something that you can still do on paper with a pencil. You can do it yourself if you're so inclined. You can look up any particular earthquake and the the S&P interval for different cities or countries, and you can get yourself a map and draw the little circles, and it's just a fun little thing to do. So there's several different ways that earthquake intensities and magnitudes are measured. We're all probably familiar with the Richter scale. It's the oldest. It used to be the most widely used. I'm sure we've all even heard the saying, that when something's really exciting, it was off the Richter scale and things of that. So it goes all the way back to 1935. It measures the magnitude of earthquakes. Um, it's also a logarithmic scale, just like the volcanic explosivity index that we learned about last week. So, what that means is if we have an earthquake that is a magnitude of 2 on the Richter scale, and then we have an earthquake that's a magnitude of 3 on the Richter scale, it's not simply one more time as great. It's 10 times greater. So, every number that we go up, we're going up tenfold in the magnitude or how bad the earthquake was. And it's also an open-ended scale. There's no top number on it. So theoretically, you could go up to 10 to a million. Of course, the planet probably wouldn't be here anymore. But in recorded history, we've never had anything greater than an 8.9. Earthquakes are rarely measured in the Richter scale anymore. When you look up earthquakes or they're reported on the news and they tell you the magnitude and give you a number, it's most likely going to be the moment magnitude. So it's considered to be a little better than the Richter scale. It's more objective. It takes into consideration more aspects of the earthquake. So it's a little better for comparing one earthquake to the other. So it considers the strength of the rock. So let's, for instance, say you have an earthquake that occurred in some granitic rocks, so some granite, which is very heavy, very strong, very dense. And then you have an earthquake that occurred with some limestone. That's very weak, very brittle, porous. So it's obviously going to take more energy and strength to break that granite than it does the limestone. So that's the first thing. They take into consideration what type of rock this is occurring in. And then they look at the surface area of the rupture itself. How big was it? How many square feet or square miles? And then the amount of displacement. So, how far did those rocks move? And that's vertically and horizontally. How many inches or feet have they been moved? So, this one really tries to measure the amount of energy that was released with that earthquake. And in the image, we can see the magnitude scale. So, again, it goes just 0 to 10, usually. And it's got some of the more well-known earthquakes listed on this image. And the third way that earthquakes are measured is with the Mercalli scale. And this doesn't necessarily measure the earthquake itself. It measures the intensity of that earthquake. How badly did it affect people and buildings? So if you had an earthquake that happened in an area, let's just theoretically say that we have this huge, really big, intense earthquake, but it occurred in an area where there was no civilization, no buildings, no people felt it. On this scale, it'd probably be a 0. But if that same earthquake had happened in a city, it could have been a 12. So this is really looking at the earthquake from our own human perspective, how badly it affected us. So if you have an earthquake that's a 1, you're not going to feel anything at all. It's just going to be recorded on very sensitive instruments. But if you have a 12, it's going to be incredibly destructive, kill a lot of people. You're actually going to be able to witness the shaking. Like when you're looking across, your vision is blurred. You can see things moving. So that's the modified Mercalli scale. Now you rarely hear about this one on the news, or if you're reading about an earthquake. If you're looking at a website or an article that's looking at the earthquake scientifically, they'll probably have this one on there. So effects of earthquakes. So we all know about the ground motion, how it affects us. It causes things to shake. We can have damage to our homes. It can be anywhere from small little cracks in the walls all the way up to giant skyscrapers tumbling down, highways coming off, just crumbling and falling. And it's very dangerous as well. People can be hit by things falling. People have been buried by rubble and died. So just the movement alone is very dangerous and causes a lot of damage. But earthquakes cause a lot of other effects and damage that we don't naturally associate with, and when we think about it, it just doesn't come to mind. What comes to mind always is the ground motion and the shaking when we think of an earthquake. So fire is a big effect of earthquakes. And in the 1906 San Francisco earthquake, the earthquake was horrible. It was a huge earthquake to begin with. But what caused more destruction than the earthquake itself was fire. So how do we get fire from an earthquake? Well, broken gas lines, fallen electric lines. Electric and gas don't go together too well. We have water mains that break. You can experience explosions, things of that sort. So fire is always a danger and a risk, especially when an earthquake hits a large metropolitan area. And landslides. So we don't want to go into landslides too much because we want to save that fun for next week. But they can be triggered by earthquakes. So when the shaking starts, any land, soil, debris, anything that's not thoroughly lithified and hard and really stuck together good, you start shaking it and it's going to come down. So in 1959, there was a huge earthquake in Montana, and it caused one of the greatest landslides in the US. 85 million tons came off a mountain and rolled down, and it covered the highway, the campsites. So there's going to be a lot more about landslides next week. So liquefaction. This is a fun one, and a lot of people have never heard of it. But it causes a lot of problems with a lot of earthquakes. So if you think about the ground, and if it's not underlain by bedrock, you could have layers of sand under there. Now, if any of you have ever gone to the beach or played with a kid with sand and you put it in a bucket and you add some water to it, you know what the water does. It goes down to the bottom and it fills in all those voids, all that porosity. But the water goes down to the bottom. And you can push down on the top of the sand and it seems pretty firm and it seems fairly dry. So you don't know that that water is lurking down there underneath it. It seems okay. And this happens in cities where people are building skyscrapers. This is a huge problem in Los Angeles. And after the 1989 Loma Prieta earthquake, there, liquefaction occurred everywhere, and that caused most of the damage. So what happens with these water-saturated sands and soils is you start shaking them up, and that water starts to move around, and pretty soon the water starts coming up, and all of a sudden your soil and your rocks and your sediment starts flowing like a liquid. Well, anybody knows that's not good under a building. You know, things are going to move with it. So here's a little video, and this guy goes out to an area where the soil appears to be really hard and firm, and he works on it. He makes his own little earthquake, and pretty soon it's liquid. So it takes a couple of minutes, but it's a fun watch. It's similar to quicksand almost. See how it's really not wet yet, but it's moving as though it were a fluid. Looks like he's having fun, but that can actually be very dangerous. So I hope he wasn't out there by himself. It can act just like quicksand, and you can get stuck in it pretty easily. But you can imagine if a building was built on a surface like that they thought was hard and firm, and then suddenly you have an earthquake and it starts to move like that. A building can topple pretty easily with that. And with a lot of earthquakes, most of the damage is caused by the liquefaction. So it's really important to know the bedrock and know where you're building. And this is one of the things that comes up in earthquake mitigation now. We have better ways of knowing where we're building and how to build. After the 89 earthquake in California, they enacted several new building codes and where it was safe to build or not. Mm, Okay, displacement of land. So we know we're moving, and things don't always go back to where they were. This image is from right outside Fort Richardson in Alaska from the 1964 earthquake. My parents actually moved there. Dad was reassigned to Fort Richardson just a few months after this occurred, and I remember Mom telling me that it looked like a bomb went off. Still, it looked like a war zone after that earthquake. Um, so, with displacement of land, the land itself can open up, it can swallow buildings, it can break roads like this. Um, you can create it can create large areas where you can't get through anymore, where you used to be able to drive, and now suddenly you got this huge open hole and you can't get to the other side. Um, it can cause a lot of problems, a lot of difficulties. Usually, the displacement is only going to be a few inches, but it can actually get up to 8 meters of movement. It can tear apart buildings and roads and pipelines. Um, and the other thing is, if you're near the ocean, this displacement and movement, if you have anything raising up underneath the ocean, you're going to displace all that water, you're going to flood land. Or if the land that's near the beach, if that sinks, you're still going to have massive flooding. So that can cause flooding to become a major effect of earthquakes as well. Aftershocks, they're pretty mild compared to the main earthquake. However, when we get to the point where we're feeling the aftershocks, we've already had those main strong destructive seismic waves. So they've weakened infrastructure, they've weakened buildings, maybe they put some cracks in a building, and now you hit it with the aftershock. So the aftershock isn't as strong, but you're hitting a damaged, weakened object. So whether it's a road, a building, you know, um, they can cause a lot of damage just because they're affecting something that's previously damaged. And aftershocks can go on for days afterwards. So what's happening is they can be little tiny earthquakes and movements. So you've had that big rupture, but now things aren't really happy where they're at. So they're still settling in, and that movement is putting out these little aftershocks. So now we come up to tsunamis. So we touched on those a little bit last week, how they can be caused through underwater volcanic activity. So anytime you have something coming up, it's going to displace that water. So think if you took, let's say you took a trash bag. Had to be a strong trash bag, but you fill it with water. And now you take your fist and you push up underneath it. Where's that water going to go? It's going to come out, right? Well, if you pushed it with enough force, instead of just gently rolling over, it would go straight up before it fell out. So you can think of it sort of that way. If you're pushing up the land at all in the basin of the ocean, you're going to push the water up. That's pretty much what a tsunami is. In Japanese, it means great wave in harbor. And a lot of people think it's like this giant tidal wave, but tsunamis are not waves at all because they're caused by displacement of the water. And waves are either caused by wind or tides are caused by the push and pull of the moon and the sun on the planet, and where we get bulges. So they're not caused by the same thing, and a tsunami is not a wave or a tide. And this is about a 3.5 minute little video, but it sums up tsunamis pretty well.
Entire depth of the water, but when it reaches shallow,
It's starting in the middle. I think the internet got stuck again. Why is it?
in 479 BC, when Persian soldiers besieged the Greek city of Potidaea, the tide retreated much farther than usual, leaving a convenient invasion route. But this wasn't a stroke of luck. Before they had crossed halfway, the water returned in a wave higher than anyone had ever seen, drowning the attackers. The Potidaeans believed they had been saved by the wrath of Poseidon, but what really saved them was likely the same phenomenon that has destroyed countless others, a tsunami. Although tsunamis are commonly known as tidal waves, they're actually unrelated to the tidal activity caused by the gravitational forces of the sun and moon. In many ways, tsunamis are just larger versions of regular waves. They have a trough and a crest, and consist not of moving water, but the movement of energy through water. The difference is in where this energy comes from. For normal ocean waves, it comes from wind. Because this only affects the surface, the waves are limited in size and speed. But tsunamis are caused by energy originating underwater, from a volcanic eruption, a submarine landslide, or most commonly, an earthquake on the ocean floor, caused when the tectonic plates of the Earth's surface slip, releasing a massive amount of energy into the water. This energy travels up to the surface, displacing water and raising it above the normal sea level. But gravity pulls it back down, which makes the energy ripple outwards horizontally. Thus, the tsunami is born, moving at over 500 miles per hour. When it's far from shore, a tsunami can be barely detectable, since it moves through the entire depth of the water. But when it reaches shallow water, something called wave shoaling occurs. Because there is less water to move through, this still massive amount of energy is compressed. The wave's speed slows down while its height rises to as much as 100 feet. The word tsunami, Japanese for harbor wave, comes from the fact that it only seems to appear near the coast. If the trough of a tsunami reaches shore first, the water will withdraw farther than normal before the wave hits, which can be misleadingly dangerous. A tsunami will not only drown people near the coast, but level buildings and trees for a mile inland or more, especially in low-lying areas. As if that weren't enough, the water then retreats, dragging with it the newly created debris and anything or anyone unfortunate enough to be caught in its path. The 2004 Indian Ocean tsunami was one of the deadliest natural disasters in history, killing over 200,000 people throughout South Asia. So how can we protect ourselves against this destructive force of nature? People in some areas have attempted to stop tsunamis with seawalls, floodgates, and channels to divert the water. But these are not always effective. In 2011, a tsunami surpassed the flood wall protecting Japan's Fukushima power plant, causing a nuclear disaster in addition to claiming over 18,000 lives. Many scientists and policymakers are instead focusing on early detection, monitoring underwater pressure and seismic activity, and establishing global communication networks for quickly distributing alerts. When nature is too powerful to stop, the safest course is to get out of its way.
So now we're going to look at a couple of active fault zones in the United States where earthquakes can emanate from. Before we get to those, I want to show you this website. I'll come back to it so you can write it down if you'd like, but let's look at it first. It has a list of all the active fault zones in the world. And there we go. So it tells you the fault, the size, the location, the type of movement, if it's active or not, and what kind of historic earthquakes have occurred there. So it's a complete list, and almost, yeah, I think all of them you can click on, and it'll give you full information about that fault zone. So if you want to look up any more information about any of the ones that we talk about today, or any of the others, this is a great resource. So I'll give you a moment if anybody wants to write that down. Okay, well, we're at a good time to take a break too, so I'll just leave it up there during the break. Uh-oh, this computer's trying to restart. Okay, welcome back. Now we're going to look at a couple of those active fault zones. Probably the most famous and the one that we hear the most about is the San Andreas Fault in California. It's a transform fault between the North American plate and the Pacific plate. So, as I mentioned last week, because of the movement, a little tiny piece of California is not on the North American plate. It's on the Pacific plate. So eventually, at some point, none of us will be around, but Los Angeles and San Francisco will wind up being right next to each other in essentially the same city. And it's a right lateral fault. So you can see from the ridge here, if you were standing on that ridge and looking across the fault, you can see that the ridge on the other side would be moving slightly to your right. It's about 750 miles long. And in an average year, without any major movement or earthquakes, it moves somewhere around an inch. So every year that goes by, if you were living in San Francisco or Los Angeles, you'd be an inch in either direction. And it's had some pretty noteworthy earthquakes coming out of that fault. In 1857, they had a 7.9 magnitude earthquake, and that's moment magnitude. It actually moved, in one event, it moved 29 feet. So that's a huge amount of movement. And then, of course, in 1906, we had the famous San Francisco earthquake, which was an 8.3 on the Richter scale. And then we had another earthquake in 1957, which was a 5.7. And 1989, the Loma Prieta earthquake, which was a 6.9. And the latest one was in 2004. It was quite a bit smaller. It was only a 6. So the New Madrid Fault Zone, it's mainly in Missouri, so it's not that far away from us. It's about 150 miles long as well, and it goes all the way from Illinois down to Arkansas. It's not a straight line, as you can see. It zigzags a little bit. It's a normal fault. Now, it's interesting about this one, it's not at a plate boundary. So it's on the interior of a plate. So what happens there is, throughout the Paleolithic history, the continent at some point had to have been stretched or maybe sutured together. Plates are not static. We don't always have the same tectonic plates. They can break into smaller plates. Plates can be sutured together as well. They can be kind of smushed up, and you can have some melting, and they can kind of, compact, and two smaller plates can become a larger plate. So when we see faulting of this magnitude and a lot of activity on the inside of a plate, we generally start to think that that's an area that at some point in geologic history was either stretched or used to be a rifting area or sutured together, but it had some kind of a plate boundary or some major activity going on there at some point. So in this area, there was a series of massive earthquakes between 1811 and 1812. One of them was so intense that it displaced the land underneath the Mississippi River, and in one location, it temporarily reversed the flow of the Mississippi. It also completely destroyed the town of New Madrid, Missouri, which is where the fault gets its name. So it's potentially, it could potentially be a very damaging earthquake if we have another big one there, St. Louis is not that far from it. In this fault line, we've had 4 of the largest earthquakes in US history. So it can produce some pretty powerful earthquakes. The last couple times it's had any activity was 1968. It produced a 5.4 out of Dale, Illinois. And then in 2008, another 5.4 from West Salem, Illinois. So enough that you could feel it, maybe cause a little bit of damage, but nothing too great. And here's an interesting story about this fault zone. In 1989, well, my dad was in the Army, so we moved constantly when I grew up every few years. And I was in middle school when we lived in St. Louis. So this was 1989, 1990. There was a self-proclaimed climatologist scientist who claimed to the entire world that all of these more recent natural disasters, he had predicted every single one of them within days or minutes of them occurring, and that he did so by watching the planets and how they aligned. And he was extremely serious about this. And he knew that the New Madrid fault was going to produce an earthquake. And he even knew the exact magnitude, the day it was going to occur. And he went to the media with it. So, being in St. Louis and being close to that fault zone, it was all we heard on the news. So, between December 1st and December 5th, we were supposed to have an earthquake that was like an 8 point something. I don't remember exactly how big he said it was, but it was going to be one of the largest earthquakes ever. So I remember being in school, and for months we were having earthquake drills. They were teaching us how to hide under our desks, how to go into doorways. We were prepared. So, being a kid, I was kind of excited. I was thinking, okay, this is going to be fun. We're going to have a big earthquake. And of course, December 1 through 5 came and went, and there was no earthquake. And being a kid and not fully understanding how bad things are, of course, I was a little disappointed that we didn't get that gigantic earthquake. I wanted to feel the rumbling, it sounded fun. But anyways, so apparently watching the planets didn't work out for him. And then after that, nobody ever heard from him again. So that's my interesting New Madrid fault story. So now we're going to take a look at a few historic earthquakes and tsunamis. So a lot of the worst earthquakes throughout history have also triggered tsunamis. So they're usually tied together. And although there's other things that cause tsunamis, they're almost always caused by earthquakes. So in 1906, we had the Great San Francisco earthquake along the San Andreas fault line. So looking back, they estimate that it was about an 11 on that Mercalli scale for destruction. The moment magnitude is 7.9, and the Richter magnitude would have been 8.3. So a very, very major earthquake. And a couple years ago, I think it was in 2018, somebody discovered this actual footage from 1906 that filmed the earthquake as it was happening. And I wasn't able to find a little short video of just that to show you, but I did find this news piece from a San Francisco local news station. And they talk about the finding of the footage, but they also show some of the footage. So this takes a couple of minutes.
is of a film
Lost piece of Bay Area history unearthed at a flea market and shown for the very first time tonight to the public.
The rare footage of San Francisco following the 1906 earthquake will end up in the Library of Congress. ABC 7 News reporter Katie Udis shows it to you first.
I knew this was going to be special.
David Keene threads the projector.
This is the way they've done it since the 1890s, really.
And he restores the films.
The Edison Theater in Niles is a historic gem in and of itself. Built in 1913, Charlie Chaplin used to watch movies here.
This premiere is of a film nearly lost to history.
This is, the missing Niles Brothers film. It's been missing for over 100 years. We know about its existence, but until now, we've not known where it is.
The Miles brothers shot Trip Down Market Street in the days before the 1906 San Francisco earthquake and fire.
They shot almost 2 hours of film after the earthquake, and very little of it survives. I think this is one of the longest surviving pieces.
The lost footage was discovered last year at the Alameda Flea Market and in fragile condition.
And I just set up a digital camera that would take a single frame for each frame of the film. And so 8,655 frames of film later, I was able to put it on the computer.
Descendants of the Miles brothers are seeing its public debut.
It's just blowing my mind. It's this whole part of my family history that I grew up not knowing about.
It's like a bookend to the trip down Market Street.
The footage will be converted back to film, so it'll last another 100 years.
It's just scary to think that there's something like that out there that we almost missed. Makes you wonder what else is out there.
After being shown in June at the SF Silent Film Festival, it'll be posted online.
It really is priceless.
For everyone to see.
In 1960 in Chile, there was the most powerful earthquake that was ever recorded. Now, Chile gets a lot of action, geologically speaking. There's a lot of volcanoes, there's a lot of earthquakes. And the reason why is they're sitting on the west coast of South America, right at a major subduction zone, a very active subduction zone. So there's a lot of movement, and it's coming from deep within the earth. So it's probably not the best place to live. But yeah, in 1960, it was the worst one ever recorded. It was a mega thrust, so that's at a subduction zone. So they're very intense. So as it's subducting down, it gets stuck, and pretty soon like that. So you get a lot of destruction from these types. It caused a tsunami, of course. And the tsunami was so great that it traveled all the way across the Pacific Ocean and hit Japan. On the moment magnitude scale, it was a 9.5. And for intensity, it was a 12. So the destruction of cities and human life, it was as high as you can go on that particular scale. It killed 5,700 people, and 58,000 homes were destroyed. And I found this little piece. It's a British news piece, but it's actual footage from 1960.
Chile pays the terrible human price it costs for the Earth itself to change its form suddenly. Rent by a series of shattering earthquakes, the land and its dwellings are crumbled and cracked. A sanctuary remains where a house of worship was partially spared, and a woman prays for lost family and friends. Nearly 5,000 are dead or missing in the disaster. Safe drinking water becomes a precious commodity for the survivors. The dangers of infection, of hunger and cold are critical for those left alive in the hardest hit cities. Foreign countries help the Chilean government with emergency supplies. The United States sends medicines, food, and clothing, in addition to doctors, nurses, and 2 fully equipped Army field hospitals. The Mercy operation helps meet the immediate crisis. Still to be faced are months, even years of hardship before Chile can expect to be well on the way to full recovery.
And if you're interested in watching more about that particular earthquake, if you go to YouTube and just search for 1960 Chile, there's a ton of videos that come up with a lot of footage, a lot of information, and some of them go into the geology of what happened as well. The 1964 Alaska earthquake was another megathrust. Alaska sits on another subduction zone. It's not quite as active as the one in Chile. It doesn't seem to cause as many volcanoes or earthquakes or to the extent that we see in Chile, but it is still quite active. And that particular earthquake was the most powerful earthquake that was ever recorded in US history. And it's the second most powerful recorded in world history. So the only one greater than that was the 1960 earthquake in Chile. So its moment magnitude was 9.2, and on the Richter it was 8.5. So it's a very, very strong earthquake. And the max intensity was in 11. So it's only one lower than the earthquake in Chile. So it caused massive destruction. And 131 people were killed. And once again, it created a tsunami as well. And it started in Shoup Bay in Alaska, and it was about 220 feet high. But the tsunami actually went all across the ocean, and it hit 20 separate countries. Now, this little video is from the USGS, so it gives some really good geological information about this particular earthquake.
Everything was in chaos. I'd never seen anything that destructive that close up.
In 1964, Alaska was shaken by the largest U.S. earthquake ever recorded, magnitude 9.2. In 1964, scientists did not understand how or why it occurred. Immediately, 3 U.S. Geological Survey scientists were sent to figure it out. There were no faults at the surface to explain it. Even with months of careful observation and fieldwork, the cause of the quake remained a mystery. Until one of the scientists, geologist George Plafker, considered the quake in terms of the newly forming theory of plate tectonics. His realization changed our understanding of these great earthquakes.
The oceanic crust is being pushed underneath that part of southern Alaska at a very low angle, and there was slip on the interface between the oceanic crust and the overlying continental crust.
These two crusts are converging at the dramatic rate of 1.5 inches each year. Periodic slip between the crusts produces great quakes, which Plafker called megathrust earthquakes. Scientists now recognize the distinctive patterns of uplift and downdrop at the Earth's surface, characteristic of these quakes.
One of the obvious things that everybody wants to know when you have an earthquake like this is how frequently do they occur? Could you have one tomorrow, or is it thousands of years?
By drilling 50 feet into the earth and taking core samples, Plafker and his team discovered 9 megathrust earthquakes had occurred in south central Alaska over the past 5,500 years. The average time span between these quakes is 630 years. The 1964 Great Alaska Earthquake was accompanied by massive tsunamis. Within minutes, one created a wave 20 stories high in parts of Alaska. Some traveled across the Pacific, wreaking havoc in coastal Oregon, California, and Hawaii. The widespread damage and loss of life from this earthquake led to a determination to use science to save lives in the future.
South Central Alaska here is the infrastructure center of the state, and it's also by far the largest population center of the state. And the work that we do, it involves basically the fundamental characterizing of the earthquake hazard, knowing which faults are active, which faults can produce earthquakes, understanding how often those earthquakes occur. And another part is understanding the local tsunami hazard.
Legacies from the 1964 Great Alaska Earthquake and Tsunami include the USGS Earthquake Hazards Program, NOAA's round-the-clock tsunami warning centers, the Advanced National Seismic System, resulting in seismic hazard maps and improved building codes. Altogether, these programs can help predict strong ground motions from future earthquakes and minimize risks. For one example, scientists learned that Valdez was so unstable and at such risk for earthquakes that the town was moved. The 1964 Great Alaska Earthquake changed our understanding of quakes and tsunamis and had a profound and lasting impact on how scientific knowledge can be used to help.
And as she mentioned in the video, that was before the theory of plate tectonics was fully accepted. And as you remember from last week, it was Harry Hess during World War II that started to put this theory together. And although the theory existed in the 60s, it wasn't widely accepted. It wasn't universally accepted until the very late 60s. So when I was getting my bachelor's degree in geology, I actually had a few professors who were working geologists in the 60s before plate tectonics. So it was really interesting to get to talk to them and find out the theories and the beliefs before plate tectonics. So that earthquake occurred at a very, very interesting time. And although it was devastating, it actually helped science and the field of geology quite a bit. In 2001, in Gujarat, India, there was a major earthquake. It was a reverse fault. And it's another interesting one because it's not on a plate boundary. It's another one that's inland, inside the plate boundary. So U.S. scientists are very interested in studying this one. It could help with some information, some knowledge about some of the fault zones that we have in the U.S. that are on the interior. So it was a moment magnitude of 7.7, and it was a 10 on the Mercalli scale for intensity and destruction. It killed a lot of people, though. 20,000 were killed, and 166,000 were injured. One of the reasons why the death toll and the injuries were so high with this earthquake was the fact that in India, at that time, they weren't building their buildings and their skyscrapers to earthquake specifications, not quite the same standards as other countries that were prone to earthquakes, like in the US, like in California. So the buildings weren't built as well for an earthquake-prone area. So there was a lot of destruction, a lot of damage to these buildings, which led to a lot of people dead. Oh. Mm-hmm. Yeah, she mentioned that it happened at nighttime, and that does really affect it as well, because people are sleeping when you start shaking, and it takes you a while to figure out what is going on. The couple of times that I've experienced an earthquake, they were very mild, and that was during the day when I'm aware of things, but it takes you a minute to really comprehend, what's going on. You kind of like, what's that? And then, earthquakes, major ones, can happen so fast. By the time you realize what's going on, things are falling. And then a more recent one is the 2004 earthquake in Sumatra in Indonesia. It was the third deadliest earthquake ever recorded. And again, this is a thrust fault, but it was between the India plate and the Burma microplate. So what a microplate is it's when a little piece breaks off of a big plate, a normal plate. So it acts like a plate itself, but it's a much smaller version of a plate. So this occurred between the India plate and the Burma plate. And a thrust fault it's just like a reverse fault, except the angle is much smaller. So instead of being maybe like that, you'll be almost flat to 45 degrees. So that's why it's called a thrust fault, because basically it looks more like one crust is being thrust up on top of the other. So its moment magnitude was 9.3. And the maximum intensity was a 9. So some of the other ones were a lot greater in their destruction, but this was still a really bad one. And it killed 230,000. And the reason why the death toll is so high is because it created a tsunami that was the deadliest tsunami in history. It reached Africa, Sri Lanka, Myanmar, Thailand. And I didn't include it, but if you want to see any actual footage of the tsunami, you can find it on YouTube. A lot of people, especially a lot of tourists who were there at the time in these countries, were filming the tsunamis coming in. And I didn't include any on purpose because it does show people getting killed by the tsunami, most of them. So it can be a little depressing. So I thought, I'll leave that part out. But if you'd like to see it, it is pretty interesting to see how the water retreats and then comes in, and how fast and how powerful it comes in. For most people, if you don't realize that it's going to occur, you can't get away from it. The interesting thing about this particular earthquake is that it affected and reached every part of the globe. Even if you didn't actually have a tsunami where you were and you didn't actually feel any shaking, it still reached there. Right here in Wichita, it reached. We may not have felt it, but it actually reached here. And our state actually rose and fell a centimeter, so it's not much, but it rose and fell a centimeter over the course of about an hour. And this happened for months. It just kept going on with the aftershocks. So if you're only moving a centimeter in about an hour, it's probably pretty impossible to recognize or feel any of that. But with instruments, it was recorded. Now, the aftershocks, they actually were felt in Alaska. So to go all the way from Indonesia to Alaska, that's a pretty strong earthquake. And so here's a video that was taken in Sumatra that shows when the earthquake actually hit and things that are shaking and falling. So it doesn't cover the tsunami. It's just going to show the earthquake.
Inilah suasana ketika gempa terjadi di Jalan Veteran Padang. Gedung yang diketahui sebagai pusat perbelanjaan roboh. Kemudian ada juga bengkel motor yang juga ikut roboh ketika gempa terjadi. Dan langsung warga di sekitar bengkel dan juga pusat perbelanjaan itu keluar dari gedung. Kemudian mereka berkumpul di jalan. Dapat Anda lihat di gambar ini, mereka sangat histeris. Bahkan ada juga yang saling berpelukan dan menangis. Namun rata-rata mereka adalah pekerja di kedua gedung ini. Dan memang gedung ini saat ini kondisinya roboh total. Karena pada saat gempa terjadi memang gedung ini langsung sedikit amblas ke dalam perut bumi.
And again, there's a lot of videos on the internet that show the aftermath. It's a little more difficult to find videos that actually show the earthquakes and the tsunamis actually occurring. Okay, so earthquake prediction. So how good are we at predicting earthquakes? Well, we've gotten a lot better, especially with technology, but it's obviously not perfect. Otherwise, there would never be earthquakes that kill people. There might be, the earthquakes would still occur. It might damage the city, but we'd be evacuated long before it ever occurred if prediction was accurate. So there's several ways that scientists try to predict earthquakes. One way that was thought to have a lot of promise was looking into the precursors or the geologic activities that occur before an earthquake hits. So they were looking at small cracks and little tremors that occur. And the problem with trying to predict a large earthquake off little tremors is, remember, the earthquake is the release of all that energy. So if you're having these little earthquakes constantly, intuitively you would think, oh, that means, the big earthquake is coming. But it actually means the opposite, that probably it's not, because the little ones, every time you have a little one, you're releasing some of that energy. So it doesn't when a larger earthquake occurs, it doesn't have as much built up energy. So you're not going to get the big one if you're having little ones that come before it. And that's not to say it couldn't be damaging, it couldn't be a larger earthquake, but if you're having smaller ones before it, it's not going to be as large as if you weren't having them. They also can look at changes in the properties of the rock, even the magnetism and different things that are happening in the rock. They thought, well, they were trying to link that to when earthquakes occur. Increased porosity or water level in wells or in the rocks. When rocks that have porosity, they have a certain amount of permeability in them. In other words, how the little holes are connected, how the water can move through the rocks. If you have a hole here and you have one here, but they're entirely surrounded by rock, that water's trapped. It's not going to flow out. So if you're having little earthquakes and you're sort of cracking that, then the water is going to have a way to come out, or even to rise up into the rock as well from down below. So any changes in the water level in wells or in these rocks, they were looking at that. They were also looking at the release of radon gas, because as you crack these rocks, a lot of them are radon containing, and they would start releasing more gas. They were looking at how in certain areas the surface of the earth is tilting or changing. So if you got things moving around, angles are going to change, how things are tilted, elevation, things are going to be moving a little bit up and down. And then an interesting one, and this wasn't so much US geologists, but Chinese geologists were looking into animal behavior as a prediction. When snakes start to leave their holes, or animals start acting agitated, or they start leaving the area. Also, a lot of native people watch the animals, and they can tell before a tsunami hits as well. So it's a good indicator, but it's not something that you can actually make a good prediction off of. So these methods, they were thought to be very promising. They were looked into, and nothing great really came from any of them. They weren't much help. So, yeah. Oh, and in the image, that is in Las Vegas, and that little thing, it records like the vibrations. And what they're hoping to do with that is, if things start to vibrate, it's like an early detection system, and they could evacuate Las Vegas. So whether that would work that way or not is yet to be seen. So there's no really good way of predicting earthquakes yet, although we are getting a little bit better. So paleoseismology. This has been the most promising so far. So what paleoseismologists are doing, so these are geologists studying earthquakes that occurred far in the geologic past of Earth. So they look at a fault line that's active, and they dig down, and they record data, and they look for signs of when other earthquakes occurred along that fault line. And they also measure some of the tectonic stress that's building up in the rocks there. And these ways are the most promising so far. And this is a little video of a paleoseismologist working along the New Madrid fault zone. And you can see how she's taking some data recordings and what she's looking for.
Scientists are investigating the past in the hope of giving people some warning before the imminent megadisaster. Scattered across the New Madrid zone, there are scars of past seismic eruptions. Sand blows that formed during the 1811-1812 quake still dot the landscape and make it difficult to grow a solid field of cotton.
The sand blows are very common, especially in the heart of the New Madrid seismic zone, close to the New Madrid faults.
Paleoseismologist Marticia Tuttle digs into sand blows, searching for clues as to the frequency of the past quakes.
I started working in the New Madrid seismic zone in 1992, and at the time the conventional wisdom was that no prior New Madrid events had occurred for 10,000 years.
Today, Professor Tuttle joins archaeologist Marion Haynes to excavate a trench in the middle of a cotton field. Digging into the soil, they uncover a very large sand blow.
The sand blow starts here. It's thin, It's getting thicker. The buried soil is about 4 feet deep. Here's another beautiful vent area. The sand blow's thinning, and it ends about there.
This sand blow is more than 63 feet wide on the surface.
The exact magnitude of the 1811-1812 events is debatable, but the effects that it had in the New Madrid seismic zone are irrefutable. And come to the field and see the ground failure that occurred, the sand blows that formed, and you'll see that these were no small events. This would be the plow zone, and that's an agricultural horizon resulting from plowing of the fields. This sand blow formed in 1811-1812 because there's essentially no soil left above it. The plowing of the fields has destroyed what little soil had developed, and it takes time to develop a soil.
Professor Tuttle suspects there may be deeper prehistoric sand blows that may hold evidence of earlier quakes. To locate older sites, she brings in a ground-penetrating radar specialist. After roping off a grid, Jamie drags the radar antenna over the ground. The radar measures soil resistance and produces this image of the subterranean world. Professor Tuttle suspects these white areas are sand blows. Excavating at this site, she finds a very unusual pattern in this sand blow. Soil with Native American artifacts, a layer known as an occupation horizon.
So as you can see, there's a great many years to go on studying these. And who knows, I don't know that we'll ever be able to predict natural disasters entirely. So some mitigation and survival tips. So the best mitigation so far has been improved building codes, stronger roofs, build on stable bedrock. But there's also base isolation, which is basically building buildings on shock absorbers. And this is frequently done now in active areas. And it's not just for new buildings. Old historic buildings, they're going down and putting them underneath. And this is a photograph of Salt Lake City and County building. And they went down, as you can see, it's a very beautiful building that they wouldn't want damaged. And they went underneath it and they stabilized it with these blocks that absorb the shock when an earthquake hits. So there's ways to build things better and help prevent some of the damage that occurs. Now, if you're ever in an earthquake, especially a bad one, and it's a possibility in this area, if you're indoors, you want to make sure that you get under a desk, a table, a bed, a doorway. You want some kind of structure over the top of you to protect yourself from things falling. And you do not want to use an elevator. If you're outdoors, of course, you want to stay away from anything that can fall on you, and this may not even be possible. In some of the videos we saw, people just scramble everywhere because it's not possible. And then you definitely do not want to drive. Don't drive anywhere. After an earthquake, if you're in your home, you want to make sure that you go and you turn your gas off. Only use portable radios. You don't want to use your electric for a little while until you know it's safe. Same thing with your water supply. And afterwards, when you know everything's safe, you want to check your home for damage or have a professional do that. Okay, so now we're going to look at a little bit of local seismic activity. So Kansas earthquakes. So now these are not earthquakes that were felt in Kansas, but these are earthquakes that actually the epicenter, the focus was in Kansas. So they were true Kansas earthquakes. So the last major earthquake that was in Kansas was April 24th, 1867, near Manhattan, Kansas. So it was due to the Humboldt Fault Zone, which is an active fault zone in Kansas. It runs all the way from Omaha down to Oklahoma City. It's right up against an ancient Precambrian anticline of granite, which is in our bedrock. And an anticline basically is when you've had compression at some point and the rocks are sort of squished and they come up into like an A shape. And the fault runs right next to that. So at some point in our tectonic history, we were very active there. You know, it possibly could have been some kind of a plate boundary at one time. But this 1867 earthquake was a moment magnitude of 5.1. So it was a good size, but not too bad. Maximum intensity was a 7. So it was very strong, but it wasn't extreme like some of the others. There were several people injured. There were no deaths from it that were recorded, but it was felt over 200,000 miles. So it produced some pretty good seismic waves. Now, even though that's a large fault and it's active, there's only a 1% or lower risk for a major earthquake along that fault zone to occur. But scientists still say that there's a possibility that it could produce an earthquake of 7.0. So that's a pretty good size. So the possibility is there. It just is very low, and that earthquake, that was the only time in recorded history that there was ever a major earthquake associated with it. Now, not far from there is the Tuttle Creek Reservoir. So if we were to have one now, it would probably break the dam and there'd be a lot of flooding. And once we're able to travel again, if any of you want like a quick little excursion, going to the Tuttle Creek Reservoir is a really fun experience, especially once you've learned a little bit about earthquakes and faults. There is an overlook that you can go to there. And you might want to bring binoculars because it is a little ways away, but you can look out and you can see this ancient fault line all the way through this massive bed of rock. So it's very interesting. It's a fun little excursion to go and do. And they've got signs up explaining the whole everything that you're looking at. So okay, these are the latest Kansas earthquakes. So even though we don't hear about it and we really don't feel it, we still have earthquakes occurring almost every day. The last few were August 3, which was a magnitude 2.4 in Smith County, and the list goes back every few days. So very, very small, uneventful earthquakes. Probably nobody felt them, but they did occur. And this is a map from the KGS, the Kansas Geological Survey, where they keep track of all the earthquakes that occur. And they have an interactive map. We're a little short on time, so I won't go there. But if you just Google Kansas Geological Survey, or if you get the slides, you can just click on it. There is an interactive earthquake map, so you can enter any date, any location in the state, and it'll show you what earthquakes and what intensities they were that occurred on that day or that time frame. You can put that you want to see magnitude 4 or greater earthquakes from this date to that date, and it'll show you where they were. So it's a fun thing. Okay, so this is the more controversial part, and people ask the question anytime I'm on the subject of earthquakes, and it's the big question of, does fracking cause earthquakes? So the answer really depends on who you ask. It's still debated. It's very controversial still, but the consensus of opinion is that the actual horizontal drilling and the fracturing of the rocks to get the oil out is not what's actually causing earthquakes. The debatable part comes in the injecting of the waste fluids into these deep wells. So according to the KGS, A bunch of geologists there published a paper in 2015 after studying this, and they state that it's still debatable. It is possible that that can trigger earthquakes, and there were 2 recorded instances of that in the 1960s that are still being studied. That was at the Rocky Mountain Arsenal and Rangeley oil fields in Colorado. So it did occur then. However, there is fluid injected into hundreds of thousands of these wells every year, and there's only a couple of them that have increased seismic activity. So it needs to be studied longer. So it's still debatable. And like I said, it depends on who you ask. If you ask an oil geologist, petroleum geologist, you're going to get absolutely no. If you ask an environmental scientist, or an earth scientist, you're going to get absolutely yes. So, but really it hasn't been proved either way. So it's a good thing to stay a little bit open-minded about and wait until it's studied a little more. And then this map here is from the USGS, and it shows the entire country and what kind of risk each area is at for having a major earthquake. So we are in the blue. So we're only 1 up from the lowest, which is gray. So we're pretty low. I mean, although we do feel them every once in a while, but we're at a pretty low risk. And before we get into questions, yesterday morning there was an earthquake in North Carolina, and it was a pretty good sized one. It was a 5.4. And as you realize, it was not along a plate boundary, so it's very similar to some of the ones that we would have around here. So you can look that up. That's pretty interesting, and it was good timing. Next week, we're going to cover landslides and floods. So now we're going to be open to questions, but we ask that for questions that there's a microphone right over here. So you can come up and ask your question at the microphone if you have any. Yes. Yeah. It's a little bit of a walk. You get your exercise before your question.
I have 2 things. First off, in Alaska, they actually have a museum in Anchorage on that earthquake in '64.
Oh.
And they show somebody that was filming a ship in a port and then it hits and it's all gone. It's very dramatic footage of that. But they have a whole kind of little museum on it.
Oh, I didn't know that. I've never been to Alaska, but I hope to at some point.
So yeah, it's very, very interesting. It's worthwhile.
Yeah.
And the other thing is the permafrost up there. We were like in Fairbanks in that area, and we kept getting little earthquakes. And I had a friend that had lived up there, and she says, even when you build your houses, that permafrost moves around. And you didn't mention that at all. And I just wondered, is that part of earthquakes? Is it just moving? What's it doing?
Permafrost and glacial movement is entirely different from earthquakes, but it is movement, and if you build on it, it's definitely a concern. So those were both very good questions. Thank you. If I ever make it there, I'll definitely check out the museum. Any other questions? Are there any emailed questions, Pat? Nope. Okay, well, thank you guys so much. And next week will be landslides and floods.